computer. We said last time, you need at least 2 papers. They have to be either journals or conferences from recent publications, and they have to be like from trusted sources like IEEE, Explorer, Elsevier, Springer, Taylor, Francis. All these publishers, they publish, we assume they publish quality papers. And we agreed also that this will count for 20 points out of the 100 that we have for this course. These are the topics. So these are actually some of the topics. You can look for whatever topics related to embedded systems. We said, I just wanted to remind you about this. We have a proposal that is due on this Wednesday through e-learning. So you need to submit it through e-learning, and I will give you approval within 2 days, whether yes, you can proceed or not. So this is regarding the proposal. We talked about the report, what is required, and the presentation. The thing that I wanted to talk about is this. Since the vacation has been extended to the end of this month, so we are going to use scenario number 2, in which the grades distribution is 15% for homeworks, 15% for quizzes, 20% for plain paper, and final 50% for the final exam. So hopefully this will not change because there are some news about the Ministry of Higher Education taking over the role of the Dean's Councils in all universities. So this might change if they decide to do that. But for the time being, we are going with scenario 2, in which the distribution is as displayed here. Okay, so I just wanted to state that.
دكتور عادي، بس شو اسمه بعد اذنك بصير نعمل شوي مدة موعد تسليم البروبوزال بدل ما هو يوم الاربعاء؟
We'll talk about it by the end of the lecture.
Okay.
Okay. All right, so let's go to our topic. We have been talking about, since 2 lectures, we have been talking about analog to digital conversion in general, and the A to D module that is available in the HCS12 microcontroller. Technically, as we said last time, some models in this, some members in this family may have 1 or 2 A to D, but they are identical. So the model that we have, which is the HCS12 DP256, which is integrated on the mini Dragon board, has 2 identical analog to digital converters. So we went through all this. We talked about the general features of the A to D. So let me just go through them very quickly. This A to D can be operated as in 8-bit or in 10-bit resolution. So the result can be represented in 10 bits or in 8 bits, and this flexibility sometimes helps us in reducing the conversion time, because if you want to present the result in 8 bits, so you need only 8 conversion cycles, while if you want more accurate result, you go for the 10-bit resolution, but you need to wait longer time, which is effectively in this A to D is 10 cycles instead of 8 cycles. We will talk about this later today, about the time that is required to do the conversion. We said that it has a sample buffer amplifier, which means it has a sample and hold circuit. You don't have to do anything external. You don't have to build the sample and hold the circuit. It has programmable sample time, or we said this is acquisition time. The sample time here, the term that is used here, it is the acquisition time, which is the time, if you remember, that you need to keep the sampling switch closed in order to allow the voltage on the capacitor to follow the input voltage. We can configure the result, whether it is 10-bit or 8-bit, to be right justified or left justified. We can control the A to D such that it starts the conversion based on some external signal or some external event or some external trigger, and we will get into more details about it. Similar to to all peripheral devices inside the microcontroller, this A to D is associated with an interrupt event, which is basically the completion or the conversion, the converging complete event. When the conversion is over, the microcontroller can be interrupted. Each of these A to Ds has 8 channels, which are connected through an analog multiplexer. So the analog multiplexer is also integrated. You don't have to use any external multiplexers. We can define what we call convergence sequences. In other words, we can specify how many conversions to perform, and we can specify whether these multiple conversions are taken from 1 or 2 or 3 or 5 channels and so on. As we will see, we can also have what is called continuous conversion, which means once you start the conversion, the A to D converter will keep repeating the conversion sequence based on your configuration. So we have 2 modes of operation. Either you do one sequence of convergence, or it is continuous. The A to D keeps repeating the conversion. And multiple channel scans, as I said, you can have the multiple samples taken from multiple channels or from the same channel. In other words, the convergence sequence could be from the same channel. You take 3 samples, let's say, or you can take 1 sample from 3 channels, which is the multiple channel scans. Okay, so these are just different ways to configure the A to D. And we said that most A to Ds, usually they come with multiple channels in order to allow the sharing of the A to D, which is a precious and power consuming device. So you don't want to have a separate A to D for each of the signals that you want to convert. So you multiplex the A to D, you share the A to D with the multiple inputs. And we talked extensively about this block diagram. And the main thing that I want to stress here is this, which is the clock. We said that any A to D conversion algorithm requires a clock because it is a sequential process. So we need a clock, and the maximum clock that this A to D can work with, as we said, we saw earlier, is 2 megahertz. Okay, but it can be less. This is the maximum clock, but you can make it less. The other thing is this, which are the analog to the A to D results registers, which are the registers that are used to store the result, and each of them is 16 bits in order to be able to store the 10-bit result. And they are numbered from 0 to 7, so that each register is associated with one of the input channels, ATD1 with analog channel 1. So the result that comes from analog channel 1 is assumed, after being converted, is assumed to be stored here by default, unless we do some other configuration to the A to D, as we will see today. So this is very important. We talked about it last time. So let's move forward. We talked about the pins. So we have the pins that are associated with the AD0 module. AD1 module is associated with these pins. These 2 pins can be used for the external trigger or for the external signal that can be used to initiate a conversion operation. Also, there are other pins associated with this module, which are the reference voltages and the power supply voltages or the pins that through which we need to power the A to D. These are separate pins than the power pins used to power the microcontroller. And as we said earlier, it is better to power the A to D directly from the power supply instead of taking the power internally from the pins that power the microcontroller, in order to avoid noise interference, especially that these voltages will pass through a digital system which has a lot of switching, which in turn will result in high level of interference. So to have a cleaner power supply, usually A to Ds, they have separate in microcontrollers that are integrated in microcontrollers. They have their own power inputs. We said this is kind of a complex module. It is associated, in order to control it and configure it and use it, there is a large set of a large number of registers. Some of these registers are for control, and through these registers you can control and configure the A to D based on your needs. There are status registers that can be used to reflect the status of the A to D module. And there are testing registers. These are for controlling and using the A to D. We have also, as we said, the results registers, the ATD result registers 0 through 7 or 8 through 15. If you are talking about the A to D module number 1. We said the pins, which are pins 0 through 7, can be the analog channels, analog pins 0 through 7 can be used as general input digital port. And in this case, there is a data register associated with these pins, similar to port A and port B, where we have port A register, port B register. And in order to determine which of these analog inputs is actually analog or it is digital, we can determine that using the A to D digital input enable. So you can use these pins as digital input, or you can use them as analog input. Okay, so let's discuss these registers in more details. The first two registers, first two control registers, 0 and 1, are only used for factory testing. So we will start from analog, from register number 2, A to D control register number 2. And this register, basically, it controls the power down, powering up the the A to D module, the interrupt feature associated with this module, and the external trigger. You can specify using this register whether there is an external trigger and what type of trigger is used to start the A to D conversion process. So if we go to the next slide, this is the A to D control register number 2. And if you remember, this X is either 0 or 1 to refer to one of the A to D modules. So the first important bit in this register that we need to use is ADPU, which is the bit that we need to use in order, we need to set in order to turn on the analog to digital converter. By default, the A to D converter is turned off in order to save power. If you are not using this module, then turn it off. So by default, it is turned off. So if you want to use it, you need to set the A to D flag. Other bits are these bits, which are used to specify whether there is an external trigger that is used to initiate a conversion process and what type of trigger. So if we go back, so there are 3 bits, which are, if you go here, this bit, and this bit. This is specified external trigger level edge control, external trigger polarity, external trigger mode enable. So this bit is important, in which you determine whether there is an external trigger or not. And if you enable it, the other 2 bits basically specify what is the type of the event that triggers the conversion. And if you go back to this table, which is the trigger configuration, This is the edge and this is the polarity. Regardless of the names, 00 implies a falling edge on analog channel 7 will start the A to D conversion process. For example, 11 on analog channel 7 can be used 11 a high level when the voltage is high at analog channel 7, then the A to D process will start and so on. Of course, this is given, this will trigger the A to D conversion process if this bit, which is external trigger enable bit, is 1, which means you enabled the external trigger. And this is an important feature, and actually it is a nice feature because you can control the A to D externally using some other system, using a switch, using a sensor, such that when there is a falling edge or a far rising edge or a logic high or logic low, you start the A to D conversion process. So this is a nice feature actually that you don't find in many microcontrollers. So these 3 bits in this register control whether you have the external trigger enabled and what is the type of the trigger. The other 2 bits which are here are associated with the interrupt. If you go here, the bit number 0 in this register is the A to D sequence complete interrupt flag. So basically this is a flag that is set whenever the A to D has finished converting the specified sequence. For example, you may specify that I want to take 5 samples from channel number 1. Once this process is over, this flag is automatically set. And if you set this bit, which is the A to D sequence complete interrupt enable bit, then this event, which is the sequence conversion complete event, will interrupt the microcontroller. And similar to any other type of interrupt, there is an interrupt vector that is used to specify the address of the interrupt service routine associated with this sequence completion interrupt event. So these 2 bits are related to the interrupt service associated with the A to D module. Whenever the specified sequence conversion is over, the flag is set, and if the interrupt enable is 1, then the microcontroller can be enabled. But keep in mind, in order to enable this type of interrupt, you need to clear the what? The I bit, right? Because this is a maskable interrupt, and this is the local interrupt enable. This is the local interrupt enable bit, which means in order to use it, you have to enable this interrupt also globally by clearing the I bit in the CCR register. Similar to what? Similar to the IRQ, right? The IRQ interrupt. Similar to the RTI interrupt. All of them are maskable interrupts. They are enabled at 2 levels, local level and global level.
دكتور
Yes.
الفلاج برضه لازم اعمل له كلير بعد ما اخلص
راح نيجي عليها. هلا mostly yes. يعني by convention all interrupt flags are not cleared on their own. You have to clear them. However, in some microcontrollers, some of the flags they are cleared automatically if the user performs some action or some event. Okay, so we will look at them. How to clear this flag and other flags related to this module.
سؤال بس بصير.
Yes.
هسه راح يصير في interrupt between كل sample وسامبل ولا السيجنال كلها لما تخلص؟
sequence يعني انت زي ما حكيت sequence شو معناها؟ What do we mean by a sequence? You mean how many conversions you want to perform. You can say I want to perform 5 conversions. Okay, this is called a sequence. Once the 5 conversions are complete, the flag is set and you can interrupt the microcontroller if the interrupt is enabled.
يعني الانتربت بس فور ويتنج يعني ما بيعمل شيء.
لا بيعمل كيف ما بيعمل، هو انتربت زي غيره.
تمام فاهم عليك، بس الانتربت سيرفيس روتين شو راح يكون فيها انستراكشنز؟
It's up to you. It's up to you. ممكن the interrupt service routine may have, for example, some instructions to read the converted values, perform some operation, perform some output operation, send the converted values to some other system. So you can do a lot of stuff in the interrupt service routine.
تمام دكتور.
So instead of having the microcontroller waiting the A to D to finish the conversion, then do whatever it wants to do, you can ask the A to D to perform the conversion, and you free the the CPU to do whatever it wants. Once the conversion is complete, you can interrupt the CPU to perform the actions required by this module when the conversion is complete. The last bit in this register is this, the AFFC, which is the A to D fast flag clear bit. So remember this bit, we will come to it when we talk about how to clear the flags of the A to D module, but this bit is the A to D fast flag clear bit, which basically allows us to enable a mode of operation in which we can clear the A to D flag bits used by performing fewer operations. We will talk about it later. This bit is not of big importance to us. Basically, it specifies what happens to the A to D module when we enter or when we put the microcontroller in the waiting mode. So if we look at this bit, which is here, which is A to D powered down in wait mode, which means is the A to D powered down when the microcontroller enters the wait mode, which is similar to what we saw earlier when we talked about the CRG block. Some of the peripheral devices, we can specify what happens in waiting mode, what happens in stop mode, and this is the bit that tells the microcontroller what happens to the A to D in waiting mode. For example, 0 implies that the A to D will continue to work normally. 1, if you set it to 1, then if you execute the wait instruction, the A to D will hold the conversion and will turn off the power completely. Okay, so it's not doing anything during conversion. So you can configure it like this. And this could be useful if you want to reduce the power consumption during the wait mode, and the conversion result is not that critical in terms of time. You can wait until the microcontroller wakes up and resumes normal operation. Okay, so this is the first register. So these registers, we need to be familiar with them because through these registers, we control the A to D. We power it up, we specify other features and other configurations. The next register, which is the A to D control 3 register, basically this register can be used to specify the sequence length. In other words, how many conversions you want to perform once you start the conversion process. It can be used to enable what is called the FIFO mode for the result registers, and it controls the behavior of the A to D in the freeze mode. Let's look at this register. So this register basically has 7 bits. The lower 2 bits basically specify what happens to the A to D when the microcontroller goes into the background debug mode. In other words, the control of the microcontroller is handled to the PC or to the host that is connected to the microcontroller, which is, as if you remember, which is something related to the SWI instruction, software interrupt, in which we handle the control from the A to D, from the microcontroller to the computer that you are connected to in order to perform debugging. For example, the code warrior, as we said, you can connect the board and you start the code warrior and you can debug your program directly when it is running on the board. So this is not that, not of big importance. What we are concerned of is this. We have 4 bits And these 4 bits, basically the SC bits, they specify how many conversions. So this is the convergence sequence length. So we have different values. We can perform up to 8 conversions, 1 conversion, 2 conversions, 3 conversions, 4 conversions. And these conversions could be from the same channel or from different channels. So basically here we specify how many conversions to perform, regardless whether they are from the same channel or from different channels. Other registers, they specify whether they are from multiple channels or from the same channel, and whether this sequence is executed once or it repeats, which is called the scan mode. Now, the last bit, which is the FIFO bit, I'm not interested in this thing that much. Basically, it specifies how the multiple results that you get how they are stored in the result registers. Okay, so it's not that big deal. Basically this bit specifies whether the results are stored in the associated registers with each channel. For example, the sample taken from channel 1 is stored in result register number 1. The sample taken from channel 2 is stored in result register number 2, and so on. Or you can enable FIFO mode, in which you can change the order or the basically the results assignment. Okay, it's not that big deal. We want to know how to perform the conversion and read the result. So I'm not interested also that much in the FIFO operation. So basically, here we can specify how many conversions we want to perform. The next register is the control register number 4, which is very important register. And this register basically is responsible for 2 main things. The first thing is the resolution of the result, which is specified using this bit, which is A to D resolution select bit. And this bit basically specifies whether the result is represented using 8 bits or the result is represented using 10 bits. And the default mode of operation is 10 bits. So by default, this register or the A to D produces 10 bits for each sample. Okay, so this is the first thing. It specifies the resolution of the result. The remaining bits are very important, and these bits control 2 things. The first thing is the frequency of the A to D converter, or the clock of the A to D converter. We said that the maximum clock is 2 megahertz. However, it can be less. And how can we make it less? Basically, by using these bits, which are the A to D prescaler bits. So these bits, if you remember the RTI, this is something similar, where you can scale down, or if you remember the phase locked loop, we have few bits that can be used to specify some scalar value to multiply the incoming clock, right? So here we have 1, 2, 3, 4, 5. We have 5 bits from 0 to 4 that can be used to specify some constant to multiply the incoming clock to obtain the A to D clock. So the A to D conversion frequency must be between 500 kilohertz and 2 megahertz. So this is another thing here. There is a lower limit on the A to D. And this prescaler is basically some value between 0 and 32, between 0 and 32. Okay, so these 4 registers, so these bits are important in this sense. They specify, they can be used to change the A to D clock. But we need to keep in mind that the clock that we have should be between 500 kilohertz or 0.5 megahertz and 2 megahertz. And accordingly, the A to D clock is simply calculated using this simple formula. Okay, so this is the first thing, the important first important thing. The second important thing here is these 2 bits, which are basically related to the sample time, or in other words, if you remember, we said sample time implies acquisition time. So if you remember, we said that the time that the A to D needs to do the conversion is basically the acquisition time plus the conversion time. So this is the time for A to D, right? So this is the time when from the moment we close the sampling switch to the moment we open the sampling switch. And once we do that, we have some voltage on the capacitor, and at that moment, the A to D can start the conversion process. So this time is basically related to the frequency at which the A to D is working with. In our microcontroller, this time, the conversion time, basically is either 8 or 10 cycles. If we are working with 8-bit resolution, then it is 8 cycles, and if it is 10-bit resolution, it is 10 cycles. So each bit requires one cycle, one A to D cycle to finish. However, how about the acquisition time? Acquisition time in this type of microcontroller is programmable. It has a minimum value of 2 cycles plus some programmable cycles. So if we assume we have 8-bit, this is multiplied by 1 over f our A to D clock. Let me write it. A to D clock, based on the formula that we have on the slide. So do you guys see the board?
Yes, Dr. Shakir.
Okay. So this value, which is basically related to the acquisition time, is programmable, and this is done using these 2 bits, SMP1, SMP2. For example, if you have these 2 bits 0, 0, this implies that the length of the second, or the value of this constant, is 2. The value of this constant is 2. If it is 0, 1, then you add 4 here. So there is a minimum value of 2, plus 2, or plus 4, or plus 8, or plus 16 cycle. So you can use this value to lengthen, to make the acquisition time longer. And why it is, sometimes you want to make the acquisition time longer? Do you remember?
عشان اكون قريب من قيمه الفولتيه اللي فعلا داخله على السويتش.
Exactly. Sometimes you want to keep the sampling switch closed longer in order to allow the voltage on the capacitor to start to follow the sample, to start to follow the input signal. Okay. However, if you extend the acquisition time, what will be the effect?
بيأثر على الفورمولا تاعت الفريكونسي الاف ام اف اس اوفر 2 راح يصير اقل من اف ام. هذا شيء غلط.
Yes, if you extend, if you lengthen the acquisition time, you are effectively increasing the total time, which is basically the sampling period. This is T, the sampling period, which is 1 over Fs. So basically, if you increase time, the sampling time, you are decreasing the sampling frequency. And if you decrease the sampling frequency, you can't work, your bandwidth, your system bandwidth will become smaller, will become smaller, so you can't work with high frequency signal, okay? So this is the idea of these 2 bits, the SMP bits. Basically, you can use them to add either 2, 4, 8, or 16 cycles to the default 2 cycle acquisition time. So in the data sheet, they say that the acquisition occurs over 2 phases. The first phase is always 2 cycles, and the second phase could be 2, 4, 8, 16 cycles, plus 8, which is the or, plus 8 or 10 bit or 10 cycles for each bit, and this is multiplied by the period of the A to D clock, like this. Okay, so these are the acquisition phase 1, phase 2, and this is the conversion time. Okay, so these are very important bits you might need to work with in order to specify how fast you are doing the convergence. In other words, how fast you are, what is the bandwidth of the signals that you are that you can work with, that you can convert. Okay.
دكتور ممكن أسأل؟
تفضل بس.
دكتور عادة الأكوزيشن والكونفرجن تو سيركتس منفصلات فممكن يكونوا بايبلاين مظبوط؟
بايبلايند
يعني ممكن أكون أنا عم بعمل أكوزيشن بس عم بعمل كونفرجن للإشي اللي قبل.
هلا بالديزاين اللي حكينا عنه لا they are not two separate circuits. الآن إذا بتطلع if you look at the diagram we have the A to D connected to the sample and hold circuit, then we have the sampling switch. Once the sampling switch opens, the circuit that which has the capacitor has to stay connected with the A to D. So you cannot pipeline, you cannot. I know what you are thinking of. You are thinking, while I am converting the sample, why not to acquire another sample? This you need to extend the design. بدك تغير الديزاين لأنه عندك كاباسيتور واحد أنت هو اللي عم بيخزن الشحنة. هلا إذا عندك أكثر من كاباسيتور and you can use it you can control them to connect to to collect multiple samples and you can switch between these capacitors. That's great. But this will complicate the design. تمام. Okay, so this is about the control register number 4, which is very, very important because through which you can specify the resolution, the acquisition time, or the value, or the value of the second phase of the acquisition time or the sample time, and the clock of the A to D. Now this table shows different values for the clock. For example, if you have a divisor, if you select this, which is a divide by 2, if this value implies divide by 2, if we go back, PRS is 0, so 0 plus 1 is 1, multiplied by 0.5, which means that the bus clock divided by 2. So effectively, the total prescaler is 2. You are dividing by 2. So here it tells you what is the maximum and the minimum bus frequency, which is the E cycle, that you may have in order to stay within the range, which is from 500 kilohertz to 2 megahertz. And this is stated here below what is meant by the maximum bus clock and the minimum. So if you opt to use this prescaler, then you have to make sure that your bus clock is from 1 megahertz to 4 megahertz in order to have a clock from 500 kilohertz to 2 megahertz. Okay. But basically, usually you have this. So you need to figure out what is the prescaler that gives you your appropriate clock. The last control register is register number 5. And in this register, basically you can select or specify the type of the convergence sequence and the analog input channel that you want to take sample from. So let's look at this register. This register basically has a set of bits. Now these bits are the channel selection bits. These bits are the channel selection bits. In these bits, you can store the channel from which the A to D has to take the sample. Okay. For example, if you store 0, 0, 0, then this implies the A to D will take the sample from channel 0, analog channel 0, when it starts the conversion, process. Okay. Other bits in this register are important. This is the mult, which is the multi-channel mode. As we said, we can have multiple conversions. We can tell the A to D start conversion and perform multiple conversions, which we called a sequence. Now, these multiple conversions, by default, they are from the same channel that you specify here using these bits. However, you can, if you set this bit to 1, you can tell the A to D to take the multiple samples from multiple channels, from different channels. For example, if you assume that these 3 bits initially have this value, 0, 0, or 0, 0, 1, 0, then if you have this bit set, for example, and you specify that the sequence length is 3, then the A to D, when instructed to start the conversion process, will take a sample from this channel, then it will move to channel 3, then it will move to channel 4 to do 3 conversion or a sequence of 3 samples. However, if this bit is 0 and you have these bits 0, 1, 0, then you will take, for example, 3 samples from channel 0, 1, 0. All right, so this is important if you are working with multiple channels. If you are working with multiple sensors that you are reading from, then you need to specify how you are collecting the samples from different channels. Either you do that automatically by setting this bit to 1, or you simply perform 1 conversion at a time. You convert from channel 1, then you start another conversion, then you start another conversion, and so on. So you do them one by one by changing these 3 bits and starting a conversion process every time. Or you just write the value of the first channel, you specify the sequence length, and you set this bit, the M bit or the multi-bit, to 1, and you start the conversion, and the A to D will take 3 samples from 3 different channels and store them in the corresponding data.
دكتور بس سؤال.
Yes.
تفضل يا زين احكي.
لا انت قبل.
دكتور ال length of sequence represent عدد السامبل that will be converted.
Yes, that will be acquired and converted.
يعني إذا حطيتها 3 sequence length 3 عادي بس باخذ 3 sample.
Yes, here in this register you specify the length of the sequence. 4 conversions, 5 conversions. In this register you specify from where these samples are collected, from the same channel or from different channel, and whether you repeat this or you do it once. And this is specified by the scan mode. Scan mode, it is a single conversion sequence. 1 implies continuous conversion. So the A to D will continuously do, let's say, 3 conversions, then 3 conversions, 3 conversions, 3 conversions, and so on. Okay, so these are the 5 bits. The remaining 2 bits are just for formatting. For example, this bit, DJM, which is the justification bit, it specifies whether your data is, how your data is stored in the data result. So if you remember that we said that the results registers in this microcontroller are 16 bits, right? But the samples can be either 8-bit or 10 bits. So we have, for example, this is ATD0 result register. ATD0 result 1 register or result 0 register. So it is result 0 register, which is 16 bits, right? It is 16 bits. However, our samples are either 8-bit or 10-bit. So how will you store them? So this is called justification. For example, if our setup is 8-bit, So each sample is 8 bits. Then you can either store the 8 bits in the lower part of the register, or you can store it in the upper part. So if you do it this way, this is called right justification. You justify it to the right. If you store it here, then you are storing it, it is left justified. That is the same thing with the 10-bit case. In the 10-bit case, we can either store the 10 bits like this, which is right justification, or we can store them here, right? Which is left justification. So it is a matter of formatting. The last bit is the sign bit, which basically specifies whether the digital value, whether to represent the sample as assigned value or as unsigned value, as assigned or unsigned value. And here I don't really want to go into details. We will always use unsigned values because the input will be scaled to match the unipolar range of the reference voltage of the ATD. However, this might be useful in some cases. However, this basically, as shown here, it tells us, for example, if you have the reference voltages from 0 to 5.12, then if the input voltage, for example, let's take this, it is 2.560, then if you use unsigned representation, if you using that bit, then this input value will be represented as 80. However, if you use signed representation, it will be 0, because this is assumed to be your 0 point, and anything below it is negative and anything above it is positive. That's why here we have, in the signed representation, we have the positive values have the most significant bit here is 0, while the most significant bit here are ones. So this is not of big deal. We will always, it can be always safe to use unsigned representation. Okay, so these are the details of the bits. So we said we have these bits. Let me go back. These bits. So these are the bits. Which channel is chosen based on the value of these bits, and so on. And here, something related to the sign, justification, and the 8-bit representation, which is already, I talked about it on the book. So this is the 5th control register. So basically we have 4 control registers. Some of them are responsible for the clock, some of them responsible for selecting the channel, setting the resolution, setting the clock, and so on. The status registers, we have 2 status registers, 0 and 1. So status register number 0, basically I'm interested in this bit, which is sequence complete flag, which is very similar to what we had in, if you remember, ATDXCTL2 register, where we have the ADIF flag, or the interrupt, or ASIF flag, which is the sequence. So this is very similar. Convergence sequence is not complete, convergence sequence has completed. So you can check whether the sequence has completed here or there in that register.
بس دكتور هذا اللي في البت او الفلاج ما بيعطي interrupt request.
Yes, it is not associated with interrupt request.
Okay.
Okay. These 2 bits related to overrun problems, and I will not get into their details. If you are interested, read about them. And these 3 bits are related to the FIFO mode, and I'm not interested as well in the FIFO mode. We don't want to waste our time in such details. But if you are interested, read about it. So this is basically kind of a counter that points to the first register to be used to store a sequence of samples. you can change it. The default, we said that if you have a result, you store it in the from some channel, you store it in the corresponding result register. However, in the FIFO mode, you can change that by basically specifying using 3 bits what is the starting register, the number of the starting register to store the result. So I don't see it a big deal in our case. So the FIFO mode, I'm not interested in it at all. This is a test register. It has only 1 bit. And basically, this register you can use as a programmer for testing purposes to make sure that the A to D is working properly. And basically, what you do in this mode, you perform a conversion. However, if this bit is selected, if this bit is set, I'm sorry, which is here, then the input value that is converted is not taken from the analog channels. It is either taken from the reference high voltage, the reference low voltage, or their average. And this is very useful if you want to make sure that your A to D is connected to the correct reference voltages and is doing the conversion correctly. Because if the input is VRH, then you will get a result that contains all ones. If it equals VRL, then you will get a result that has all zeros. If it is the halfway between the minimum and the maximum, then the digital result will be right in the middle. For example, if you are talking about 8-bit, then the result should be 100000 or 80 hexadecimal. And how you specify whether you are converting this or this or this is basically through the channel bits that are in the control register number 5. However, they will not be taken from the corresponding analog channels. They will be taken from these values because this bit is set. If you set this bit, you start a conversion with this channel selected, you are basically converting the high reference voltage for just testing purposes. Status register number 1 is very simple register. Basically, we said we already have basically we have 2 flags to indicate that the sequence conversion, the conversion sequence has completed. However, is there a way in which we can know if a conversion from a certain channel has completed or not? Actually, in this microcontroller, yes, we have this register which has 8 flags, conversion complete flag 0 through 7. So basically, these flags are set whenever you finish a conversion from the corresponding channel. So for example, if you have specified a sequence of 3 from 3 channels, 0, 1, and 2, the flags we discussed earlier, they will be set when you finish the whole sequence. However, these flags will be set when you finish the conversion from the corresponding channel. But these flags are not associated with interrupt events. You cannot interrupt the microcontroller when you finish one sample, for example, in a sequence from one channel. You can only interrupt when you finish the whole sequence, okay? So these flags can be used to know whether the conversion from some channel X is over or not, okay?
يعني دكتور بقدر اعتبره بس فور مونيتورنج، يعني اكيد اذا الهول 1 هذول الثلاث اكيد راح يكونوا 1 صح؟
Exactly. بس فرضا انا I want to know to do something when the conversion
from channel 0 اعمل شيء معين.
Yes. Okay. However, if I want to perform something when the whole sequence is completed, yes, I need to use the other the other flag. And one more thing, if I want to use interrupts, these flags are of no use because I cannot interrupt the microcontroller using these flags. The only way to interrupt the microcontroller from the A to D is using the using the sequence completion flag. Okay. Okay. Now, important thing related to these flags is how to clear these flags. And here are 3 different ways to clear these flags. Basically, if you write to the control register number 5, all of these flags will be cleared. All these flags will be cleared. And basically, writing to the A to D control 5 register initiates the conversion, starts the conversion, because if you remember, this register, control 5 register, has the channel number. So if you write to this register, basically you are telling the A to D, start the conversion from this channel. So if you do that, basically you are clearing these, these flags will be cleared automatically. Another way is basically you perform a read to this register, followed by reading the result from the A to D result register. So basically, you can clear these flags by reading the status register and reading the result. This is if this bit, if you remember, we talked about it in the second, in the control 2 register, automatic fast flag clear, which is false here, or 0. When it is 0, means that in order to clear these flags, you need to perform these 2 operations. However, if you set this flag to 1, only a read to the corresponding result register will clear the corresponding flag. So, for example, if you have this mode is set, fast flag clear, and you want to clear CCF4, you just go to the result register number 4, and this flag will be automatically cleared. Okay, so these are different ways to clear these individual flags. How to clear the interrupt flag that we talked about earlier, basically by writing a 1 to it, similar to the RTI flag that we saw earlier.
دكتور شو بقصد بأحكي ريد؟
ريد يعني تقرأ الفاليو من الريجستر وتجيبها على السي بي يو مثلا، تحطها بدي ريجستر أو بالإكس ريجستر أو بالواي ريجستر. This is what is meant by a read. Okay. The last 2 registers, or the last register, control register, it is the digital input enable, and I talked about it. Basically, using this register, you can specify which of the pins or which of the analog pins are used as analog or digital. So you can specify them individually. Some of the pins you may configure them as digital, some of them you configure them as analog, and those who are configured as digital, if you perform a read on these pins, their values will be stored in the A to D port data register, PTAD register. So this is called port PTAD0. So it has a PTAD0 register to store the data if one or more of the pins or the analog channels are used as digital. The last set of registers are the data registers, which we already talked about. 16-bit registers divided into 2 8-bit registers, the high register and the low register, and we talked about them when we discussed the justification thing. Okay. Most of what is coming, I talked about it, so I will pass over them very quickly. Here he talks about the analog multiplexer, few notes, the input signals that I need to keep in mind. They have to be unipolar and they have to fall within the potential range between VDD and VSS analog, or the power supply of the A to D. In other words, what does this imply? That the reference voltages, they have to be in this range as well. And thus your signal has to be in this range. Okay, so V reference high and V reference low should be between VSSA and VDDA, or the supply voltages for the A to D. The A to D clock, we already talked about it, how to select the clock, how to prescale the clock, how to specify the acquisition time, how to specify the resolution. And this is very important that we need to keep in mind is the range of operating clock of the A to D. This is how to calculate the conversion time, which is very similar to what I wrote on the board. Basically, it is the number of bits in resolution, which is either 8 or 10, 2, which is the default or the minimum acquisition cycles, plus certain number of programmable cycles that you can add to the acquisition time divided by the clock frequency. So this 2 is the for the first stage of the acquisition. For the second stage, it is programmable using the SMP bits that we saw earlier in the 4th control register. Here's a simple table to do some math. For example, if the clock is 2 megahertz and you are using 8-bit resolution, then the time that you need to do the 8-bit conversion basically is 4 microseconds, because the cycle is half microsecond. It is 1/2 megahertz. So half microsecond times 8 is 4 microseconds. This is the conversion time. Then the acquisition time could be this, or could be this, could be this, could be this, which is always 2 plus some value. So it is 2 microsecond, because we have 4 times 0.5, which is 2 microsecond, and so on. So this is the conversion time. This is the acquisition time, which is programmable. It could be this case, or this case, or this case, or this case. And each time it is computing the acquisition time for the maximum clock frequency and the minimum clock frequency. So let's assume, let's take an example, a very quick example. Let's assume that you are working with 8-bit resolution, okay? You are working with 8-bit resolution and 2 megahertz. You are operating at 2 megahertz, which is the maximum ATD clock. If I ask you what is the maximum sampling, what is the maximum sampling period, and what is the minimum sampling period? We said the sampling period is basically the conversion time plus the acquisition time. So if I'm talking about the minimum sampling period, the minimum sampling period, it will be what? 4 microseconds plus 2 microseconds, right? This is the minimum time in which you can obtain the 8 bits that represent the result when the clock is 2 megahertz. So this is T minimum. Okay, this is T minimum, the minimum sampling period. So the minimum sampling implies that Fs is what? Fs will be 10 to the power 6 divided by 6, right? Okay, okay. I'm using a touch screen, but it is not that accurate. Okay, so the maximum sampling frequency will be 10/6 megahertz, will be 10/6 megahertz, right? Because this is in microsecond. But if this is the maximum sampling frequency, then the maximum FM, in other words, the maximum frequency of the incoming signal is basically half this, right? Which is 10 to the power 6 divided by 12. We said that in order, according to the sampling theorem, in order to be able to represent a signal, your sampling frequency should be less, should be maximum, should be twice the maximum frequency content, or the frequency content of the signal should be half the sampling frequency. Okay, so this is basically, this is your bandwidth, the bandwidth of your system. In other words, the maximum frequency that you can feed to your A to D. How about the minimum, the maximum T? Same thing. For Tmax, Tmax will be 5 microseconds for conversion. Okay, for 8-bit, sorry. We are talking about 8-bit. So 8-bit at 2 megahertz is basically, we have 4 4 microsecond for conversion, T max, maximum sampling period, plus this 9 microsecond, which is 13 microsecond. So basically, your sampling frequency will be the minimum here. Your sampling frequency will be 10 to the power 6 divided by 13, and accordingly, your maximum frequency in the input signal will be 10 to the 6 divided by 26. So of course, the bandwidth here will be less. In the previous case, it was 10 to the power 6 divided by 12. So your bandwidth is higher in the first case. However, the accuracy of your converted value in the previous case will be less because you did not give enough time for the capacitor to follow the voltage, the input signal, okay? Here, in this case, when you operate in this case, your results will be more accurate because the acquired sample is closer in value to the input signal. So the conversion result is closer to the actual value. Okay, so this is your bandwidth in this case. So this is FS minimum, right? This is FS minimum.
دكتور بس سؤال.
Yes.
هيك انا اللي بتحكم في الاف ام، يعني المفروض انه حسب الاف ام انا اعمل ادجستبل الاف اس. انا شايف العكس.
ما هو انا هون عم بحسب لك الماكسيمم والمينيمم كيس. اذا انا ما if I can't operate as a sampling frequency, I can't work إلا بهذا الvalue. Then this implies that I cannot feed the system with a signal that has a frequency greater than this value.
فهمت عليك تمام. يعني انا بحدد الستاندرز وبعدين بشوف ايش الانبوت سيجنال.
Usually it is this way. So that's what you have sometimes on some devices when you are working with analog signals, devices that work with analog signals, like the oscilloscope, digital oscilloscope, for example. If any of you worked with a digital oscilloscope, it tells you what is the bandwidth of the system, what is the maximum frequency that this device works with, because it needs to convert it. So there should be a maximum frequency in the input signal, because I cannot work with a sampling frequency larger than twice than of this value. Okay. Here is just an illustration about what we just talked about. This is the acquisition time, which is 2 phases. This is 2 cycles, and this is programmable. As we said, we could be 2, 4, 8, and 16. And this is the conversion time, which could be 10 or 8 cycles, depending on whether you are working with 8 bits or 10-bit resolution. And once this time is over, the CCF flag is set here. And here we say the CCF flag of the channel, which is in the status 1 register. And if this is the sequence, if the sequence is basically one sample from one channel, then also the sequence completion flag will be also set. Okay. This is another feature in the A2D, which is the wraparound. And basically, if you are using the A2D to acquire multiple samples, so you have a sequence length greater than 1, and you have set the multi-bit. In other words, your sequence will be taken from multiple channels. For example, let's assume you started the conversion of 5 samples. Okay, 5 samples from a channel number 5. So the A2D will start conversion from sample number 5, and it will store the result in register number 5. Then it will take sample from channel 6. It will store the result in register 6. Sample from channel 7, it will store the result in register number 7, result register number 7. However, the sequence is not over yet. We still need to take 2 more samples. So these samples will be taken from 0, 0, 0, and from 0, 0, 1. And this is what is meant by wrap around. When you reach to 1, 1, you go back to 0, 0. This is what is meant by wrap around. And this only happens, this will only happen if you have the multi-bit set, because you are collecting channels from multiple samples. Now, what if the channel, the samples are taken from the same channel? For example, 5 samples from the same channel. So you are basically, for example, taking samples from channel 0, and you are taking 5 samples. So the first sample will be stored in register 0, right? The second sample from the channel will be stored in register 1, and then 2, and then 3, and then 4, and so on. Okay, so if you have multiple convergence from the same channel, they will be stored in different registers in the same order, starting from the register that is specified or assigned or related to the input channel. Here we have an example that is similar to what I had shown. Basically, it tells us if the SC bits in this register are 0, 1, 0, 1, and the channel bits in the control 5 register are 1, 1, 0. What is the convergence sequence for this setting? So basically, these bits, if you go back to this register, specify the starting channel. So the starting channel is channel 6. And if you go to the control register number 3, these bits tells us that we need to perform 5 conversion. So the sequence length is 5. So we will store in start from 6, then we'll go to channel 7, then we will go to channel 0, then channel 1, channel 2 to perform 5 convergence, because this is the sequence length. And that's what we have here. The convergence sequence is as follows. And this is what is meant by wrap around. What is the time? Okay, this is the external trigger. We talked about it. Signed and unsigned control. We said that we are only concerned with unsigned numbers. And this is the power modes for the A to D. So basically, the A to D can be either turned on or turned off. So here it says that the power down mode, basically the A to D is turned off. So basically this mode can be entered by basically clearing the power up bit, which means turning it off, using the stop instruction. So when you enter the stop mode, the A to D is turned off, because if you remember in the stop mode, all the clocks are stopped. So the A to D clock is killed, so there is no A to D operation. So basically the A to D is turned off, or by executing the wait instruction and having this bit, if you remember, we talked about it, in this register set to 1. In other words, the A to D is in power down mode in the wait mode. The important thing here is whenever you power up the mic, the A to D, or you, in other words, you go from the power down mode to the run mode, you need to wait 20 microseconds before using the A to D to perform conversion. And this is essential in order to allow the A to D to stabilize, because there is some transient period, there are resistors, capacitors, you want the system to stabilize. So you need to delay using the A to D for 20 microseconds before you start the conversion. The run mode, which is the normal mode in which the A to D is powered up and you use it to do conversions. Idle mode, the A to D is basically powered up, but you are not using it to perform conversion. And this could be inefficient, especially for long periods of time, because the A to D is powered up and it's consuming power, but you are not using it. So it is very important that You put the A to D to power down mode whenever you are not performing convergence, especially for a very long time, because there is power consumption here, but it is near maximum. Here we have maximum power consumption in the run mode. Okay, what's the time? أنا المشكلة هون ما ببين عندي لأنه full screen. اللي أطلع. Discard. Oh, okay. So we went over time. So next time we will continue. We have few things left, basically examples on how to use the A to D, how to write a program to use the A to D, to configure the A to D and use it to perform some convergence. Okay, so so these are the steps, general steps. So we'll take 2 examples in C and assembly and see how to program the A to D. What I want you to do is basically, if you have some time, is to read or to go through these through these sections, which are basically examples on how to interface the A to D to some sensors. I think there is a light sensor, there is a temperature sensor, pressure sensor. So these sections, each of them discusses one example on one type of sensors and shows how to write a program to control or to interface to this sensor. So look at them. It doesn't hurt. You will get more better idea about using the A to D. All right.
الله يعطيك العافية دكتور.
الله يعطيك يا رب.
دكتور مروان بداية المحاضرة حكى لك عن موضوع التيرم بيبر.
تمام.
يعني أنا قرأت يمكن شفت 6 من